Hi, I'm Matt Venn. I've been involved in the open source silicon movement for about the last 4 years. And in this presentation, I'm going to give you a bit of context, the history. I'm going to signpost the best resources and the best tools to get started and give you a few demonstrations. And I'm also going to show you a project that we've made called Tiny Tapeout that lets you take your silicon designs and get them manufactured onto a real chip that you can get in your own hands to play with and test. So let's get started. This is my first chip design that I made 4 years ago, and one of the things that surprised me when I got started was just how small my FPGA designs were. So this is an example of a project that I made, a clock that shows a time on a VGA panel. And because it was so small, I reached out to some friends of mine and we put 8 designs on and multiplexed them with this multiplexer. All of them go into this area here, which is about 10 square millimeters. And then we have the pad frame and this RISC-V coprocessor that is provided by eFabless. And they do the multi-project wafer service. They send this off to Skywater in Minnesota in the United States, and then they make the chips and send them back to us. So to give a bit of context, I really got started in 2020 when Google and Tim Ansell and eFabless announced a free shuttle opportunity. So if your design was open source, you could send it and get entered into a lottery, and if you got lucky and won the ticket, your chips would get manufactured. And that included not just the manufacturer, but also the open source tools and the open source PDK. The PDK is like a database of all the things that you need to know to design a chip. So I made my VGA clock, which was running on an FPGA. I ran it through the tools and I got a result. And I thought, great, I'm going to go and do this. There was a Hackaday SuperCon, which is another great conference. I'm a big conference fan. And there, in the pandemic, I did a remote presentation about what I'd learnt on the ASIC side and asked people if they'd be interested in a course. And I got a few hundred people saying they would be interested in paying for a course, so I started the Zero to ASIC course then. I did my first tape out with that clock design in December with eFabless, and in February I launched my course. eFabless run a system called Chip Ignite, that's their paid for multi-project wafer service. So for $10,000 you can send your design, it doesn't need to be open source, and you get 100 chips back. So it's about $100 per chip, and you get 10 square millimeters. So this is about 4 to 10 times cheaper than the normal industry rates, and you don't need to sign an NDA, and you can use open source tools. In June we had the MPW2 tape out. We received MPW1 silicon in October, and there were some real problems with that. We were mostly able to work around them, but these issues were introduced by some tool chain problems. As we got started, the tools had some configuration problems that we didn't realize until later. And so the first 5 runs were all affected in various ways. So MPW 1, 2, 3, 4, 5 were all a bit difficult to get started. I did another presentation at the end of 2021. I received my chips in the previous year, but I only got them working in 2022. It took quite a lot of effort. In March, my course submitted a design where we started putting more and more designs on, and this has been a constant theme for me, wanting to get the most benefit from the silicon area, so precious. We had another tape out in June, and in September I tried my first tiny tape out. So the idea is a lot of people submit designs that are actually very small, so why don't we try to fit as many designs as we could, and I was aiming to get 500 designs on there. So that was a free project. I opened it up and we maybe got 160. I got the stats, I'll show you later. Global Foundries is another process, 180 nanometers, and the PDK was also released and made to work with the open source tools. So we had 2 more Global Foundry tape outs and 1 more Skywater tape out at the end of 2022. In January, we launched Tiny Tapeout 2, which was a paid version. So you paid for a little slice on this tile, and then we got guaranteed silicon by working with eFabless. So that was really good for me, because one thing I'd been annoyed by was the lottery system. I wanted to be able to pay some money and definitely get the chips back. But $10,000 is too much for me and for most of the people that I was working with. So by slicing up that chip into 100 pieces, we were able to spread the cost and start manufacturing with guaranteed silicon. Now, we also were expecting another MPW, because they were happening once every quarter, but in April there was nothing announced. So that was a bit of a premonition that maybe things weren't going to go so well with their free lottery shuttles. MPW 6 hot lot received. A hot lot is where you pay extra to get your chips run through the foundry quicker. And that was to check that all the fixes that had been made on the tools and the Caravelle harness from MPW 1 to 5 were all fixed. And the great news was that from MPW 6 onwards, everything worked perfectly. So that was fantastic. In October, we did a live stream tiny tape out silicon bring up, which was quite hair raising. Most companies will tell you that their chips work first time, but that's a lie. Most of the time they fail. They do another revision and they fix the bugs. So we were very pleased that things worked. But one of the things that we're doing with open source silicon is to try to learn and fail more in the open, to show people what's going on behind the curtain. So we decided to do a live stream silicon bring up, probably the first one that's ever been done. If you want to check that out, you can click this link. The presentation slides will be available from the Embedded Online Conference website. And there was another Global Foundries tape out. And I haven't updated this for April. Not too much has been happening in terms of tape outs. We heard from Google that there was going to be, they finished their sponsorship. There's not going to be any more MPWs from them. Maybe someone else will step up. And we've now done Tiny Tape Out 5 and 6. So that's a good route of actually getting designs manufactured. So a few words on the community. The community is one of the great things that the open source tools offer. Is normally in the industry, everybody is very siloed and specialized. Things are secret and it's difficult to share information. With the open source community, we have nearly 7,000 members on the Open Source Silicon Slack channel. The tools are all open source and you can read the source and contribute. And we have more PDKs coming. Two quite interesting ones are the IHP 130 by CMOS, which is great for analog, works at very, very high speeds. And Pragmatic is a UK foundry. They're planning to open source their PDK, and they have a very interesting process that is quite limited, it's quite slow, but you can get your chips made in just a few weeks in comparison to a few months from a traditional PDK. So pretty interesting for the educational side of things, I think. So in my journey, I've been meeting a lot of interesting people. I recently interviewed Dr. Carsten Wolf, who's teaches at university and is also principal IC scientist at Nordic Semi. And in his opinion, there's nothing blocking the use of open source tools for chip design. It's just a matter of time for us to build the trust and grow the library of IP that we need to do cool and interesting projects. If you want to watch that video, check this link. So I promised I would give you a tool interview and signpost you to some good resources. So we're going to do that now. And I just got another quote for you here. Somebody that I know who needs to remain anonymous, who works for one of the world's largest chip design firms. One thing that's great about open source tools is it makes self-study much more possible. So chip design has traditionally been something where you do at a university level, but you don't really get good at it until you join a big company and you get access to the tools and you get mentorship. And I think that this is changing now that we've opened access for people who aren't in industry, who aren't in academia, to still get involved. So you can click on this link and get a full list of a few hundred different resources. The most popular and most used end-to-end digital ASIC flow is called OpenLane. There's also OpenLane 2 that has just been released. It depends on OpenRoad, which is a DARPA-funded project that contains many of the key tools inside. And the idea is that you can put in your hardware description language like Verilog or VHDL, and at the end you get the GDS files you have to send to the factory. There's also one called Silicon Compiler and another one from the EU called Coriolis 2. Yosis HQ makes Yosis, which is a synthesis tool used for FPGA and ASIC flow. And Yosis HQ also builds this OSS CAD suite, which is a single binary download that contains a wide range of digital design tools, makes it easy to get set up and started quickly. Now on the analog front, we have layout tools provided by Magic and K-Layout. NetGen is for layout versus schematic. That's checking that after you finish your layout, it matches your schematic. Xscheme is being used for schematic capture, and ngSpice and Zeiss are both used for simulation. If you want to programmatically generate your GDS, you can use GDS Factory. And there's an interesting full wave solver, which is pretty important for higher frequency stuff, called OpenEMS. Now, we've got a lot of ground covered, but there's still quite a lot of stuff missing. And from the experts that I've been talking to, these areas have been identified as needing room for improvement. So, especially for high frequency things, we don't really have much in the way of RFIC design tools. So even though we've got this very, very fast IHP PDK coming, it might be quite difficult to do radio applications without good open source radio design tools. And one example is we can't do inductance extraction. So after you do a layout, you want to extract the circuit from the layout to simulate it. And at the moment, the tools that we have can't do inductance extraction, and that's definitely important for radio. We also only have a limited type of analysis that we can do with ngSpice, and we've got some missing. Especially important is transient noise, I've been told. Some of them exist, but we don't really know how reliable they are. So this is something that will be filled in as we get more silicon back and as we do more characterization. There needs to be better mixed signal co-simulation support. So that's when you've got mixed signal, you've got some digital and some analog, and you want to simulate them both together. ngSpice 42 is the latest one, and that now does support Verilator, which is another open source simulator. And that can be used for co-simulation. I've just been testing that myself. We have a tool called Fault, which does scan chain insertion, but it's not currently in a usable state. And scan chain, if you're into embedded, you know what scan chain is. And when you're designing your own chips, ideally you want to put a scan chain in there so that if something goes wrong, you can find out more easily what's gone wrong. Or in the better case, things go right and you want to test everything. You can test things more easily inside the chip with a scan chain. Now with our PDKs at the moment, 130 nanometers, we don't really have too much of a problem with power voltage drop across the power distribution network, but this will grow in importance as we get access to more modern nodes. And the same goes for clock distribution and simulation. One of the first issues that we hit with MPW1 was a problem with clock distribution. There was too much clock skew across the chip, and that caused an issue. And we didn't have the tools to verify that. And another thing that's missing is proven analog IP, and this also goes for digital IP. We have thousands of designs now that have been sent for manufacture or are in process of being manufactured, but we don't really know how much of it is good, how much of it has been really tested, how much of it has been characterized. And especially for analog IP, it's expensive and long-winded to characterize. However, there has been some recent progress in this area, and one of the great things about the Tiny Tape-Out project that I'll explain more about is that we put lots of designs on one chip, so that makes the testing more easy to spread between multiple people. So another quote from a friend of mine called Jörn, who used to be in industry doing audio ASIC engineering for a Danish company, and he has now become an independent ASIC engineer. So there's a new type of freelance engineering that's happening now due to the open source tools, and he's able to work with custom projects for clients. He hasn't been able to share me much information because the work that he's doing is not open source, but he's able to do the initial work and sometimes all of the work with the open source tools. So this is unlocking some good and interesting new ways of working. So we also have new tools, and this is a tool that I've been involved in developing. I developed it with Uri Shaked, who's a co-collaborator on Siliwiz and Tiny Tapeout. And this is a great way of getting started to understand the fundamentals of what's going on at the transistor level of semiconductors. So we can take a quick look here. So we've got all the lessons here: introduction, draw resistor, parasitics, voltage dividers, and so on until you get up to a CMOS inverter. And here we've got a NMOSFET. So we can see how they're laid out with this little drag. I can see the cross-sectional view here. I've got the gate coming in. It drops down to this polysilicon over here. And then I've got my source and my drain and the substrate underneath. And then in my simulation, the blue is the input voltage to the gate, and then the orange curve is the amount of current that's allowed to flow from the source to the drain. And this is all in the browser, so you don't need to download any tools. It's really great for education. We used ngSpice compiled to WebAssembly, so all of this works very, very nicely and interactively. And you can even experiment, see what a thinner gate means to the performance of the MOSFET, go through the lessons, build up to understanding how an NMOS works as an inverter. As the input rises, the output goes low. Unfortunately, NMOS uses quite a lot of current, so that's why we moved to complementary MOSFETs, CMOS. And so a CMOS inverter uses a P and an N, and we get this sharper, more efficient curve. So you can play with all of this in the tools, in your browser. Don't need to download anything, and all the lessons are available here. So great, I've signposted you some getting started places for tools, but what are people actually building with these tools, and how relevant are they to you and what you're interested in? I thought I'd showcase some of my favorite example projects. So this is a microcoded USB peripheral. You can load in the type of endpoints that you want, and then it deals with the timing part. Here's a 5 GHz satellite transceiver, just the beating heart of it, the PLL. And the author of this project, Thomas Parry, has started a startup called Spherical Systems, doing custom silicon for space-rated projects. And he's using the open source chip tools. He's based in the Netherlands. If you're interested in working on a startup like this, get in touch with Thomas. Fuse RISC, very interesting. 2 RISC-V processors with some custom embedded FPGA fabric. Subservient is a 1-bit serial RISC-V processor. We've seen a lot of interest in AI and accelerating AI recently, and one pathway to do that is by doing it in the analog route, not the digital route. So this is an example of an analog neuron. Very impressive RISC-V with a 5 GHz embedded transceiver. If you remember that Nordic Micro, who do a lot of IoT and embedded radio stuff, they only moved from 130 nanometers a few years ago. So the 130 nanometer processor is still very, very useful for mixed signal radio. An 8-bit A to D, a RISC-V Arduino, so an open source Arduino. This is a great project. A Delta Sigma audio DAC from JKU University. Microwatt, different type of processor from IBM. OpenFASOC is an interesting way of doing analog, but kind of in a digital way to make it more automated. And Dr. Harold Prettel, who's the lead of the university who made this, is now using the open source tools with his students. And he says it's a great way of getting involved and into the industry unburdened by NDAs or software license terms. So let's say that you're interested, you want to get involved, you want to make a chip and you want to see this whole process through. What is the easiest way of doing it? Well, we've made a project called Tiny Tape Out. I referred to it earlier in the presentation, and the whole idea is to split the cost of one chip in between many people to make it cheap enough to make it affordable. And ideally, we want everybody who's doing an undergraduate degree in computer, chip design or VLSI to be doing a tape out. Shouldn't have to wait for a PhD. And it would be great if people who were normally excluded, which means almost all of us, had access to this. So if you think that just 10 years ago, PCBs were very difficult to have access to, very expensive. The tools cost a lot of money. And we've had a huge renaissance in the open source PCB tools, what kinds of things people are doing with them. And we want to do the same thing with silicon. So at the moment, we're targeting makers, schools, hackerspaces, and entry-level digital design courses, and anyone who's an open source silicon enthusiast. And we do have also interest from industry, but as we make everything open source, sometimes people prefer to go straight to eFabless and pay the $10,000 for a private, non-open source shuttle run. So you can get started with this tool called Wokwi, which is an online tool, also by my colleague and collaborator Uri Shaked. And everything in between these two green plates will be manufactured in the chip. And we can add more components down here. These are our standard cells, our logic cells that we can use. We have 8 inputs, 8 outputs, and then 8 bidirectional pins you can use as you wish. And after drawing a circuit here, you can also simulate it in the browser. So this is for a simple puzzle. I have to set the inputs correct to get that output light to come on. So this goes to an AND gate. We've got one side that's already on. This other side must be off. So this one's got to be 0, and that one's got to be 1. So I can set these here, 0, 0, 0. That's all being turned into 1s here. Set this last one to 1, and then we get the light coming on and this segment being lit. Now I can take this number up here and then plug that into the Tiny Tape Out GitHub action system, and that will make the GDS files that we need to send to the factory. And after we do that, we get a layout like this. So if I go to the GitHub repository now, so you clone a template repository, you take that number and you paste it in here. And then once you commit, it runs the GitHub actions, and we have a GitHub action called GDS. If you're not familiar with GitHub actions, it basically gives free cloud compute for open source projects. So this uses a couple of our actions to first build the GDS and then build the viewer. And if you want to see how that happens behind the scenes, all of our infrastructure is open source. If you go to the Tiny Tape Out GitHub organization, you'll find it there. So let's see what happened. We had 194 microns of wire, hardly any utilization. You can see all of this is empty, and just the little bit of that is needed to do the design is up here. And we also have this cool 3D viewer, which is what I took the screenshot from over here. So I can hide all the filler cells, unused cells, and I can hide the power and the wiring. And I can see that up here is where things are at. Over here I've got the stats, and I can see that this is really the only gate that is being used. So my 6 gates here are being condensed down by Yosys synthesis tooling to just this one gate here, and I can isolate it now. And then if you've played around with Siliwiz, you'll be able to have a better understanding of what's going on. But we can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 transistors here, connected with this local interconnect, and then powered with these 2 bars here. All being part of this big circuit, connected with power lines. These big blue lines are the power distribution network. And then that fits into the big tiny tape-out chip that includes around 500 tiles, about this size. So that all happens with the GitHub project, and crucially, you don't need to install or download any tools. So that can be a very difficult stepping stone. It is easier and easier to install the tools these days. It used to be a lot harder. But especially if you just want to try this out without that install step, or you're doing a workshop with some colleagues or some students, you can try this without having to install any software. So the kinds of projects that people are doing on Tiny Tape-Out, linear feedback, shift registers. You can click on any of these links and have a look at them, and even simulate them. LED drivers, binary coded to decimal counters. And then when you graduate from Wokwi, which is perfectly fine for learning with a few gates, I probably wouldn't want to draw more than this. Then you move to a hardware description language like Verilog, VHDL, Amaranth, and you can build CPUs, RISC-V processors, and even FPGAs. We've also just enabled mixed signal designs. So this is a 555 timer, fully analog. And Vincent Fusco, the designer, who's a professional IC designer, really likes the open source flow, and is super happy that he can now do analog mixed signal tape outs for less than $1,000. So we've really smashed down those high barrier to entry. So the stats of the project, that we just closed Tiny Tape-Out 6, which was our best run so far. We filled 100% of the shuttle with 237 projects. And you can click on these links, see what the designs are. The green ones are the analog projects. You can click on one of them and it will take you to the actual design in process. And there should be a bit of information about how it works and how to test it. Let's pick one of these other ones. This is one of mine. RGB mixer, how it works, how to test it, what the pin out is. And then all of this gets combined into a data sheet so that we have one big data sheet with all the designs for this one chip in it. We've got the chips working. We did a very hair-raising live stream, but luckily for us, the chips worked, and we have sent out Tiny Tape-Out 2 and Tiny Tape-Out 3. People are testing their designs, and BitLooney did a really fun video about the chip that he made, the best chip in the world. So if you want to find out some more information, see a fun video about people making custom chips, then check that video out. And this is the product that we ship. So you get one chip with your design and everyone else's design on it. We have an RP2040 coprocessor that allows you to plug it into the computer with a web USB and then simulate the inputs and capture the outputs. And this is showing setup for my VGA clock that I have on my desk right now. And that's the end of my presentation. Tiny Tape-Out 7 is open now. If you want to get involved and make a submission, you've got 40 days left. I've got a newsletter. I've got an in-depth course called the 0 to ASIC course, and I really enjoy connecting with people. I'm on LinkedIn, I'm on Mastodon, and I'm on Twitter. So thanks very much for listening to my presentation. I hope that you learned a lot and you're inspired to have a go, get involved in the exciting world of open source silicon. And I just want to say thanks very much to the Embedded and Online Conference for inviting me. And I'm very happy to have done this presentation.